You're able to see the screen now?
Yes, sir.
Okay. Okay, so this is what is the relationship between mu2, m2 and m1. Okay, so mu2 equal to m2 minus m1 square. Okay, so this m2 is our mean square value. Okay, so the same thing I've expressed in terms of the expectation symbol, that is e of x minus e of x the whole square is equal to e of x square minus e of x the whole square. Okay, so this is a very important relationship. Okay, so you'll be seeing this relationship in the next two chapters also. Okay, so the same formula you'll be using to find out this mu2. Okay, and then we saw one example of evaluating the moment. Okay, so evaluating the variance. Okay, so this was our first example where we saw we were evaluating the variance of an exponential density. Okay, so the density function that is given here, it is an exponential density, that is 1 by b into e power minus of x minus a by b. Okay, so when we evaluated this moment, that is the variance, okay, we had to go through a lot of integration, right? So we used so we were having this expression, we made a small substitution to make it into a standard form. Okay, so we to make it into this standard form, that is integral of x power n into e of ax dx. Okay, x power n into e power ax dx. Okay, so to bring this in this standard form, we made a substitution x minus x bar the whole square equal to zeta. Okay, and then we made all the corresponding changes for other terms in the expression. Okay, so and then we used the standard result. Okay, so if you can recall, so this is the substitution that we made. Okay, so that enabled us to convert this integral into the standard form. Yes. Okay, so this is the standard form that we brought that integral to. Okay, so we have a constant term outside, so that into integral zeta square into e power some constant into zeta d zeta. Okay, so we used our standard result, so where this the constant term is minus 1 by b, instead of x here we have zeta square. Okay, so this is our standard form. Okay, so this standard form has an expression. Okay, so we have this expression, that is this integral x power n into e power ax dx equal to e power ax into the whole bracket x square by a minus 2x by a square plus 2 by a cube. Okay, so once we have this in standard form, we are able to substitute that. So now all the expressions are in terms of x bar. Okay, so everything comes in terms of x bar. Now we go to our previous example where we have already found out the x bar of the exponential density and distribution. Okay, so this x bar was already evaluated in the previous example, that is equal to a plus b. Right, so this x bar we already know that it is a plus b. Now we are going to substitute in this complete expression only the value of x bar. So our entire expression reduces to the form b square. Okay, so we used a plus b everywhere wherever x bar occurs, and we are able to cancel out a lot of constants. So now it is mu2 equal to b square. That means the variance of an exponential density is nothing but b square, where b is the constant that is coming in the exponential density function, that is 1 by b into e power. So this is the b constant, e power minus x minus a divided by b. Right. So we'll see another example today for the same evaluation of moments. Okay. So this is example 2. Okay. So this is the screen visible?
Yes, sir.
Yes. Okay, so this is our result of the previous example. Okay, so this is sigma x square. The same can be even represented by mu2. Mu2 is same as sigma x square. Okay, that is equal to b square. Mu2 equal to b square. So this was the result of This was the answer to the previous example. Okay. Now we go to the second example. Okay, where we are asked to find out the skew of an exponentially distributed random variable x, described by we know what is the expression for exponential distribution, 1 by b into e power minus of x minus a by b for x greater than a and 0 for x less than a. Okay, and we are also asked to find out the coefficient of skewness. Okay, so we know that there are two terms, one is skew and the other is coefficient of skewness. Okay, what is this coefficient of skewness? Skew is nothing but our mu3, right? What is coefficient of skewness? Just recall from the last lecture. It is mu3 divided by root of mu2 the whole square. Sorry, this is root of, just a minute.
mu3 by sigma
Sigma cube. Sorry, this is cube. Root of mu2 the whole cube. Okay, so this is the coefficient of skewness. Okay, so once we know mu3, we know what is mu2 from the previous example. Okay, we can just make the cube of it. Okay, so that is already we know that mu2 is equal to b square. So root of mu2 will be b. So this will be b cube. Okay, so we can evaluate what is the coefficient of skew once we know what is the value of this mu3. So what is this mu3, which is skew? So skew, which is equal to mu3, it is equal to expectation of x minus x bar the whole cube. Okay, so what I'm doing here, I'm just expanding it, a minus b the whole cube formula. So I'm just using that formula inside the bracket. Okay, now I'm going to apply this expectation operation to each of the terms inside this bracket. Okay, so e of x equal to x bar. So what I'm doing is, so I'm putting the expectation here, and for each term. So what I'm getting here, so e of x cube, so that I'm putting as x cube the whole bar. Okay, so I'm just simplifying the notation. Okay, so instead of putting e of x cube, I'm putting x cube the whole bar. This is also a valid notation. And this is same as x cube the whole bar. Okay, so just to avoid clutter here, I'm just using a different notation. Okay, so minus 3x bar x square. Okay, so what is this x bar? X bar is a constant, right? So when you x bar is already an expectation, that is an expected value. Now we are again taking expectation for an expected value, that same constant result. Okay, so it is 3 into x bar into, we have an x square here. Now we are going to take expectation operation only to this term. So what happens? It becomes x bar the whole, x square the whole bar. Okay, so 3 into x bar into x square the whole bar. Right? So here what happens? So we have x bar the whole square here. Is that clear? It is 3x bar the whole square into x. Right? So your x bar the whole square, that is also a constant. Okay, so what you have here, you have 3 into x bar the whole square into again x bar. Right? So are you able to follow this? So this is 3 x bar the whole square into x. Okay, you are applying the expectation operation for this term. Okay, so what happens? 3 comes as it is. X bar the whole square, that is also a constant, so it comes as it is, x bar the whole square. Now the third term, that is your e of x. Again, if you change the notation for this, this is equal to 3x bar square into x bar. So what is this effectively? It is 3x bar the whole cube. Okay, is it clear how this becomes 3x bar the whole cube? Okay, so we have 3x bar the whole cube. So we have another term minus x bar the whole cube. That is minus 1 x bar the whole cube. Okay, so it is essentially 3 minus 1 into x bar the whole cube. That becomes 2x bar the whole cube. Is that clear how we are reducing this to this? Okay, yeah, when we are applying the expectation operation to each of the terms that is inside, this is our resulting expression for mu3. Okay, x cube the whole bar minus 3 x bar into x square the whole bar plus 2 x bar the whole cube. Is that clear? So you have to clearly know the difference of each term here. Is that clear up to this point? So yeah, if you have any doubt here. So it is just a change of notation, that's all. Okay, so we are not doing any big calculation here. Okay, so just to have a simplified notation, I'm putting all e of x into x bar. Okay, so now I have this complete expression. Okay, so okay, I'll make it more clear. Here maybe a little bit confusing. Okay, so this is mu3 equal to x cube the whole bar minus 3 x bar x square the whole bar. Okay, so are you able to see the difference between x square the whole bar and x bar the whole cube? Right, so this is plus 2 x bar the whole cube. Okay, so the bar is coming below and cube is coming above. Okay, so here square is coming below, the bar is coming above. Okay, can you see the difference? Right.
Yes, sir.
Yes. Okay, so this is, so you have to note down this expression correctly. Okay, so when you're reading this slide, you note down this expression correctly. Okay, so you have to write and see, otherwise you will not write it in the correct way. Okay, so when you write, you will notice, you'll get the practice of making the difference. Okay, yes. So now the first term in the LHS. Okay, so this we don't know what is this value, x cube the whole bar, right? So till now we have not evaluated this value. Okay, so now this we can observe the second term, means the second and the third terms. Okay, so this is, so as you can see here, so this is x square the whole bar, right? So x square the whole bar. So if you write this as mu2 equal to m2 minus m1 square. Okay, so this x square the whole bar. So what is that? That is your m2, right? So this x square the whole bar, that is your m2, correct? Right. So what you can write in terms of mu2 and m1? So you can bring m1 to the other side. So what happens? Mu2 plus m1 square, that will be your m2. Is that clear? I'll not include this bracket. Okay, so I'm just bringing this m1 square to the other side. Okay, so this is minus m1 square, on this side it is plus m1 square. Okay, so mu2 plus m1 square is your m2. Okay, you already have one m2 term here. Okay, so just it is given in different notation, but it is the m2, right? So that thing I'm writing it as 3x bar into this one, mu2 plus m1 square. Okay, so I'm just giving in different notation so that you'll have practice of different notation. So what is this mu2? This is nothing but sigma x square plus what is m1? That is x bar. So that is x bar the whole square. Okay, so sigma x square plus x bar the whole square, that is equal to m2. So that I am bringing in here. Okay, so this is because of this formula. So this is the same as this is mu2 equal to m2 minus m1 square. Okay, so why we are writing in this terms is we know this value. Okay, so already from the previous example we know this value and this value. Okay, so this value is also known. Okay, so we are bringing in terms of known values, right? So we have one more term left out here, so that is 2x bar the whole cube. So we know what is x bar. Okay, so x bar is also known, that is the mean value of the exponential distribution. We know that x bar is equal to a plus b. Okay, so we are bringing all the terms in terms of known values. All right, so only thing that needs to be evaluated is this x cube the whole bar, that is expectation of x cube. Yes. Okay, so other terms are known, so I'm leaving it out. I'm just taking the first term, that is x cube the whole bar. Okay, what is x cube the whole bar? E of, so just recall what is x cube the whole bar. Just go to my Okay, so we'll just take this as example 2. This one. This is our evaluation of moments. So this is example 2. This is our example 2. We are evaluating the skew of exponential random variable. Okay, so I'm directly going to start from this. Okay, that is x bar the whole cube. So we now want to evaluate x bar the whole, sorry, x cube the whole bar. I'm just confused. This is x cube the whole bar, which is nothing but expectation of x cube. So what is the expectation of x cube? Just you use the definition of expectation, integral minus infinity to plus infinity, x cube into fx of x dx. Okay, so this is by our basic definition. You have to recall. So recall the first definition of, or the basic definition of expectation. Right. So we have, what is this fx of x? So we have integral minus infinity to plus infinity x cube by b. We have 1 by b into e power minus of x minus a divided by b. So this is x cube by b into e power minus of x minus a divided by b into dx. Right. Okay. So and then now we have to change the limits. Okay, because this function is valid only for x value is greater than some constant a. Okay, so it will be a to infinity. So this becomes, so the limits are changed to, change from a to infinity. Okay, they are from a to infinity x cube by b. Okay, so now it is already in the standard form. Okay, so we have integral formulas for e power, sorry, x power n into e power ax dx. Okay, so we have a standard expression for this. So this I have already given here. Okay, so here instead of n we have 3 x cube into e power some. Okay, we have to write first, make this integral into this form. Okay, so there are some constant terms which you have to take outside. Okay, if I expand this integral, it will be from a to infinity x cube by b into e power minus 1 by b x. Right, so this is x into 1 by b into e power plus a by b. Right, so I can make this e power plus a by b to come outside. So e power plus a by b divided by b into integral a to plus infinity x cube into e power minus 1 by b x dx. So there is a dx. Okay, so now is this in the standard form? We can compare this with the standard form. Okay, so this standard form has a formula. So this formula I have to memorize. Okay, so this is the standard result, x cube into e power ax. Okay, when the n value equal to 3, you have this, you have to memorize this complete expression. Okay, so it is x cube by a minus 3x square by a square plus 6x by a cube minus 6 divided by a power 4. Okay, so you will not, in exams you will not be asked to evaluate problems using more than this power of x. Okay, so you will not be going beyond x cube. Okay, so it is better to remember the formula up to this value, that is x cube into e power x. Okay, in the appendix I think it is given up to x power 5. Okay, so it is just enough to remember up to x cube e power ax. Okay, so what we are doing, we are just evaluating this. Okay, so this integral is evaluated using this result. Okay, so you can take that as an exercise. Okay, so you can just evaluate this, and final answer after substituting the limits. Okay, so that will be equal to a cube plus 3a square b plus 6ab square plus 6b cube. Okay, so what I am telling here is, so you have to use this formula. So you are going to use the standard formula for integral x cube into e power ax dx. Okay, so here the a value equal to minus 1 by b. Okay, so it becomes, so using the standard result, so using standard result, okay, so this becomes, that is e power a by b divided by b into, so you are going to evaluate this. Okay, so this will come out to be, so some term in x. Okay, so x cube by a minus 3, so all these terms will come. Okay, I'm just giving a rough picture here. So x cube by a minus 3 by a square, correct? 3x square by a square, sorry. So 3x square by a square plus 6x by a cube plus 6x by a cube minus 6 by a power 4 minus 6 divided by a power 4. Okay, so actually this a here is minus 1 by b. Okay, so you'll be writing minus 1 by b. So this is minus 1 by b whole square. So this is minus 1 by b the whole square. So again here it is minus 1 by b the whole cube. Here also minus 1 by b the whole power 4. Okay, so you have to simplify this expression first and then you have to apply the limits. Okay, so this is plus infinity to a. Okay, so when you apply this limit, so your final expression, so that will turn out to be, I think I missed one e power ax here. Okay, so there is another e power, I didn't, so there is an e power ax outside. Okay, this is e power ax into these terms. Okay, so I'll change that. Okay, so please note that this is e power a by b divided by b into e power ax into all these terms. Okay, so what happens here, we have instead of a, here we have e power minus 1 by b x. Okay, minus 1 by b x into all these terms. Okay, so when you substitute plus infinity, that is the upper limit, so this term makes everything to be 0. So are you able to follow? Okay, so it is e power minus bx into all these terms. Okay, so you are applying the limit for this entire term. Okay, so when you apply the plus infinity limit here, so it becomes e power minus infinity, making everything 0. You just have the second limit. Okay, so it is e power a by b divided by b into e power minus of a by b into all these terms. So you have a minus sign outside because upper limit minus lower limit, you have a minus sign outside, and this becomes a cube divided by, or a cube into b. Okay, so minus of a cube into b. So like that you have all the terms. Okay, so when you okay, this outside term, it gets cancelled. Okay, so this is e power plus a by b, e power minus a by b. So you have just 1 by b outside. Okay, so after substituting all the values, the final value that you get, final expression that you are getting is this one, a cube plus 3a square b plus 6ab square plus 6b cube. Okay, so I'm not showing all the steps in between. I'm just showing the final result. Okay, so you can work out this problem and you can just verify whether you are getting the same result. Okay, so this will be a practice for you in integration. Okay, so just evaluate this and see what is the final expression here. Okay. Okay, so now we know this value x bar. Right, so right now we have evaluated what is this x cube the whole bar. Okay, so this is e of x cube, and we, from the previous example, we know what is this x bar. Okay, now we are going back to the previous expression. Okay, so this expression mu3 equal to x cube the whole bar minus 3 into, so okay, so this we can substitute for the second term. Okay, so we know what is this x bar value, so that we are substituting for the third term. Okay, so now we are directly going to evaluate this mu3. Okay, so mu3 equal to x cube the whole bar minus 3x bar into this value plus 2 x bar the whole cube. Okay, so you know what is this value? Just now we found out. Okay, a cube plus 3a square b. So this is the entire value that comes for this term. Okay, we know what is x bar. Here it is a plus b. Substitute a plus b here. Okay, so sigma x square we know that is equal to b square. Okay, so this into b square plus x bar the whole square. So what is that? So, so this is x bar the whole square. So that will be a plus b the whole square. Okay, again 2x bar the whole cube. Right, again 2 into a plus b the whole cube. So you substitute all these values, you finally simplify it, what you will be getting is mu3 equal to 2b cube. Is that clear? So I'm not showing all the steps here. Okay, you have to go through all the steps and finally your mu3 value turns out to be 2b cube. Okay, so this is your skew. So what is this value? This is your skew of exponential distribution or density. Or you can also say exponential random variable. Okay, so this is skew of exponential random variable. Okay, now we want to evaluate the coefficient of skewness. So already we evaluated what is the denominator. Okay, so that is sigma x the whole cube. Okay, this is same as your root of mu2 the whole cube. Right, so that is equal to b cube. We already have a b cube here. So what is the coefficient of skewness? So coefficient of skew, that is equal to 2. Okay, so the value of skew is 2b cube. Okay, the coefficient of skewness is 2. Right? So you can just compare this coefficient of skewness with the previous discussion. Okay, so we have already seen this in the previous slide. Okay, for different skew, how does the curve looks like? Okay, it's taking some time to open. Okay, so on this is 14, right? Okay, so you can recall this slide. Okay, here we are not showing any numerical values here. Okay, so this is the skew. Okay, so this is the coefficient of skewness. Okay, so what we got is a positive skew, right? So we have the coefficient of skewness is +2. Okay, so that means it is a positive skew. So positive skew means so it is all the values they are skewed towards the left side. Okay, so this is the type of curve that we are having for our exponential density. Okay, so if we got a negative number here, that is -2, so our curve will be looking like this. Okay, so this is just to compare your skew value with the type of curve that you are getting. Okay, so if you are not getting anything for skew, if it is a 0 skew, it will be a symmetric curve. So now I think we are in lecture 15. Oh, so we evaluated mu3 equal to 2 BQ. Okay, and our coefficient of skewness was equal to 2. So it has a positive skew. So obviously our curve will be looking like this. Okay, so it is all the values move towards the left side. Okay, so now we have done 2 examples. Okay, so we can recall our first example and this example. So what we are observing is that, so there are some observations to make in these 2 examples. Okay, so what we are observing is that moments about the mean. Okay, so that is all the mu's. Okay, so mu1 or mu2, mu3, mu4. So all these things, okay, they can be evaluated once we know the moments about the origin. Right. So if we want to evaluate mu2, okay, we have to know what is m2 and m1. Right. So we already saw this formula. Right. So if you want to evaluate mu3, okay, I'll write here. So if you want to know mu2, it is enough to know m2 and m1. Okay, so if you want to evaluate mu3, you should know what is m3, m2 and m1. So mu4 you will need to know m4, m3, m2, m1. Okay, so that is what we saw this for the case of mu3, right? The evaluation of mu3, it took into account this m3, m2 as well as m1, right? So evaluation of this m3 was the most tedious one, right? So we had to do a big integration and evaluate what is m3. Okay, other expressions we already had the result m2, m1. Okay, so if you go for mu4, you have to evaluate using a big integral what is this m4. Okay, and then already you have this result m3 and then m2, m1, etc. Okay, so this is the first observation. Is that clear? Is it clear to you what is the observation that you are making here? To evaluate any mu, you need the same number of m, small m, and the lower numbers. Okay, so for mu3 you needed m3, m2 and m1. Mu4 you needed m4, m3, m2, m1. Okay, so we need to have the knowledge of all the moments about the origin that are at the same level and below that. Okay, that is the first observation. The second observation is that evaluation of moments of higher orders, that is n greater than 3, it becomes tedious as integrals of higher powers of x are involved. Okay, so here we had to evaluate x cube into e power ax dx. Right? So since this is in the simple e power ax form, we had a standard form and we evaluated it. Okay, so if this is the density function, right? Whatever comes near x cube, so that is the density function. Okay, so since this was a simple density function, we are able to use our standard result. Okay, if you have some other expressions, okay, x cube into this fx of x is some very complex. This one, say tan inverse of x or inverse of x by b, something very big. So you'll be doing even bigger integrals. Okay, so that becomes tedious. And suppose this x power also increases, it will be like x power 5 into say tan inverse of x by b dx. Okay, so like this, I'm just giving an example as tan inverse function. It can be any function. Okay, so it can be a sine function. Okay, sine of x by b or cos square x by b. There are a lot of different functions which we can use it as density functions. Okay, so you have to evaluate some big power of x power 5 or x power 6 into something, and you have to find out the answer. Okay, so that means the integrals are very tedious. Okay, so in the evaluation of moments, up to moments of order 3, it is easy to evaluate. Once we go above order 3, it becomes very tedious to evaluate. Okay, so that is the observation. Okay, so now for this reason, mathematicians found out some solutions which are known as characteristic functions and moment generating functions. Okay, is that clear? What are the two observations that we made here? So this is the second observation. Yes. So what are the observations for from the two examples that we have done? Yes, one of you can give an answer. See, we have done two examples for calculating moments. Okay, our first example was calculation of variance. The second example was calculation of skew. Right, so what were the observations in these two? You already have here, right? So for calculation of any moment mu3, that is moment about the mean, we need to know m3, m2 and m1. Okay, if it is mu4, m4, m3 and m2, m1. So all the lower moments have to be known. Lower moments about the origin has to be known, and the same level of moment it also has to be known. Okay, mu3 means we know we should know m3. Okay, and evaluation of this m2, m3, m4, this is a very tedious integral. Okay, so evaluation of these numbers m2, m3, m4, it requires big integrals. Okay, so that is the difficulty in evaluating the moments. Okay, but when you're asked to evaluate moments for mu3 up to mu3, you have to use this method. Okay, so in exams you have to use this method. There is no other way to evaluate the moments. Okay, so when you are asked to find out moments greater than mu3, okay, you have to go for another method which are known as, we have to use some other functions through which we can obtain moments by taking derivatives, and those functions are known as characteristic functions and moment generating functions. Okay, so now we'll see what are these characteristic functions. Okay, so a characteristic function of a random variable x, it is defined as phi x of omega. Okay, so this is a capital phi. Okay, so this is capital phi, so this is a small phi. Okay, so phi x of omega is equal to expectation of e power j omega x. Okay, where j equal to root of -1, you know, that's a complex number, and omega varies from -infinity to +infinity. So why omega is a real number? So omega is a real number between -infinity and +infinity. Okay, so this is a definition. This is a definition of characteristic function. Okay, so in terms of probability density, it can be written as, so what is expectation of e power j omega x? So e power j omega x, it's also a function of x, right? So previously, if you can recall, so expectation of x, we have a formula, and expectation of any function of x, g of x, we have a formula, right? So what is e of x? E of x equal to integral -infinity to +infinity x into fx of x dx. What is e of g of x? It is integral -infinity to +infinity g of x into fx of x dx. Okay, so now instead of g of x, we have e power j omega x here. Okay, so our g of x here in this case, g of x is e power j omega x. Okay, so this is also another function of x, right? So this is also one function of x. So like g of x can be, say, x square. So this is also a function of x. Okay, g of x can be 2x cube plus 3x square. This is also another function of x, or g of x equal to sin x. So these are all functions of x. So similarly, e power j omega x, this is also a function of x. Okay, so now we are taking expectation of that. So what happens to this expression? That is this one, e of g of x. So that will be integral -infinity to +infinity fx of x into e, or means I'm just writing it in this second place. Okay, so always this comes here. It is e power j omega x into fx of x. Okay, so just for clarity purpose, I'm just bringing this to the next to fx of x. Okay, so this is according to, so this expression. Okay, so this is according to this definition of expectation of a function of x. Is that clear? So our characteristic function phi x of omega, so that is equal to integral -infinity to +infinity fx of x into e power j omega x dx. Is that clear? So only difference between this and this expression is, here the g of x is coming next to fx of x. Okay, so actually this should come here. e power j omega x. Okay, I'm writing this after fx of x. Okay, so the order doesn't matter. Is that clear? Okay, so now this function, this phi x of omega, so that is known as our characteristic function of x. Okay, so now why we are going for this characteristic function is, so now evaluation of moments becomes easy. Okay, so when you are going for higher order moments like greater than mu3, okay, now you can just evaluate that moments by taking the nth derivative of this characteristic function. Okay, so that is the application of this characteristic function. Okay, so now that we know this phi x of omega, okay, so what is written here? The nth moment about the origin can be obtained by differentiation of the above expression n times with respect to omega. Okay, and then setting omega equal to 0 in that derivative. Is that clear? See, as you can see in the previous slide, for mu3 we needed m3, right? So for mu4 we will need m4. Okay, so for instead of evaluating mu4, it is just enough to evaluate this m3, m4, etc. Right? So you have a density function, exponential density function. Okay, use that to find m1. Okay, and then m2, and then m3. Combine all three, m3, m2, m1 to find out mu3. Okay, so and then you just evaluate m4, combine all these four. Okay, so this is just a algebraic combination, right? So you are just using some algebraic method to combine all these, and then you can evaluate mu4. Okay, so instead of doing integration many times, okay, you are just doing integration just one time to evaluate your characteristic function. So this is the only integral you have to do. Only integral to be evaluated. Okay, once you evaluate this integral and keep this function with you. Okay, so this phi x of omega. Okay, so it is a one-time job. Okay, so just once you evaluated a difficult integral and you find out this phi x of omega. Okay, so after that, to find any higher order, sorry, to find any higher order moment, you are just taking the derivative of this phi x of omega for n times. Okay, so taking derivatives is lot more easier than taking integrals. Okay, so taking derivatives is lot more easier than evaluating integrals. Okay, so any derivative we can calculate very fast. Okay, so compared to integrals, taking derivatives is, it is very easy. Okay, so we go for this method of taking the derivative and substituting omega equal to 0 in that nth derivative. Okay, so you also note that there is minus j power n in front of this. Okay, so mn equal to minus j whole power n into d power n phi x of omega divided by d omega power n. Okay, so this is the nth derivative. Is that clear? Okay, so these two are very important formulas that you have to note down. Okay, so this one and this one. Okay, so this is the formula for finding out the nth moment about the origin. Okay, so note that this is not mu n, this is mn. Okay, this is the nth moment about the origin. Okay, why we are not giving formula for mu n? Why we are not giving formula for mu n? Why only for mn? Yes. Yes, why we don't have formula for mu n? Because once we know mn, we can combine all mn, mn minus 1, mn minus 2, etc. up to m1. Okay, so all this can be combined to find out what is this mu n. Okay, so that's why we don't have formula for mu n, we just have for mn. Okay, so this is the characteristic function and its method of evaluating the moments. Okay, so now similar to our characteristic function, you also have one more function that is known as moment generating function. So we have another function known as moment generating function. Okay, so that is also another expectation. Okay, so as you can see here, it is denoted by capital M, mx of v. Okay, so this is a small v, mx of v, that is equal to expectation of e power vx. So what is the only difference? So previously it was expectation of e power j omega x, that was a complex number. Here you have just e power, it is expectation of e power vx. Okay, so this is a real exponential. Okay, so v is a real number from minus infinity to plus infinity. Okay, again we are using our definition of this expectation. Okay, so that is, this is taken as the function of x. Okay, that into density of x integrated from minus infinity to plus infinity. Okay, so this we are using. So using the definition of expectation. Okay, so again from this we can calculate the nth moment about origin mn just by taking its derivative n number of times and then substituting v equal to 0. Okay, so why we are having two functions, both characteristic function and moment generating function, is for some density functions we will not have this moment generating function. Okay, so this moment generating function does not exist for some of the density function. Okay, so some random variables. Okay, so for that we go for characteristic functions. Okay, so these two functions help us in evaluating the moments in a easy way. Okay, so we need not to do complex integrations. Okay, so we can just do simple derivatives quickly and find out what is the value of each of the higher order moments. Okay, so okay, so there is one example I have given for calculating moments using characteristic function. Okay, so I'm taking the same complex exponential distribution. Okay, so the same as example 1 and 2, I'm taking the exponentially distributed random variable. Okay, so that is 1 by b into e power minus of x minus a divided b. Okay, so the same function. Okay, now we can see how it becomes easy for us to calculate up to moments of mu3. Okay, so up to the value of 3, we are able to calculate mu just by using our characteristic function. Okay, so what is the first step? What is the expected value and variance of exponential distributed random variable? What they are asking is, so expected value means it is m1 and they are asking mu2. So for mu2, what are all the things required? What are all the moments required for finding mu2? Yes, what are the moments required for finding mu2? Just recall from the previous example. See, mu2 means we need to have m2 and m1, right? So the same order in m2s, okay, and then m1. If it is mu4, m4, m3, m2, m1. Okay, so you have to, if you want to find mu2, you need to have m2 and m1. You are going to combine this and find out what is mu2. Okay, mu3, you need to have m3, m2, m1. Okay, all three you are going to combine and find out what is mu3. So similarly it goes on. Alright, so now we want m1 and, so just it is enough to evaluate what is m1 and m2. Okay, once we know these two, we can easily evaluate mu2. Okay, so first step is to create the characteristic function. Okay, you have to first make the characteristic function, use our integral. Okay, so phi x of omega is equal to integral minus infinity to plus infinity. So this is your fx of x, that is 1 by b into e power minus of x minus a by b into e power j omega x dx. Okay, so here I can multiply the terms inside. So this becomes e power minus 1 by b x into e power plus a by b. So all the constant terms I'm taking outside. So inside you have integral a to infinity e power minus 1 by b minus j omega into x dx. Okay, so this integral, so integral e power ax dx is nothing but, so this is a basic integration formula. This is e power ax by a. Okay, so this is the result. So I'm using, so this entire thing is the constant term here. It is e power ax divided by a, evaluated between infinity and a. Okay, so you apply these limits, you get this function. Okay, what is this function? Now what is this called? Yes, you have to answer. What is this function called? Yes, Manikant.
Sir,
What is the function that is in the box? What is the name of that function? Are you all following? Yes, students, if you have any difficulty in understanding this, you please tell me now itself. What is the function? What is this function called? Yes, who else? Meher? Yes, are you able to follow the class? What we are discussing today?
the characteristic function.
Yes, very good. It is a characteristic function. Okay, so this is our characteristic function. Why we are finding out the characteristic function? What is the use of finding out this function?
Simplify in the evaluating of the moment.
Yes, your voice is breaking. Yeah, why we are finding out the characteristic function?
Evaluating of the moments.
Very good. So it is for evaluating the moments in a easy way. Okay, so using the direct definition of moments, it is a difficult method. Okay, it can be used only for finding moments up to n equal to 2 or n equal to 3. Okay, when you're evaluating moments for n value greater than 3, your direct method of integration, that becomes a difficult method. Okay, so that is why you are going for this characteristic function. Okay, so once you make the characteristic function, so once you know this is the characteristic function, for evaluating say fourth moment, what you are going to do? You are going to take the derivative 4 times. Okay, you are going to differentiate this function 4 times, and you are substituting, you are going to substitute omega equal to 0 in that final result. Okay, so if you want to get the fifth moment, you are going to take the derivative 5 times. Okay, so taking derivative is more faster and easier than taking integrals. Okay, so that is why we are going for this characteristic function method to evaluate moments. Okay, so now we know this is our characteristic function, e power j omega a divided by 1 minus j omega b. So this is our characteristic function. So what we need actually, we need m1 and m2. Okay, so that is what we are asked to. We are asked to find out these two parameters, m1 and mu2. So first we want m1 and then m2. m1 m2 can be combined to form mu2. Okay, so m1 can be taken by taking, it can be found out by taking first derivative. Okay, so you have to recall the derivative formula. It is u by v method. Okay, so that is d of, if you are evaluating the derivative of, so u of x by v of x. Okay, that is d by dx of, so this is a standard formula in derivative. Okay, so v into du minus u dv divided by v square. Okay, so that is a standard formula in derivative. Okay, so you have to memorize these formulas for derivative. Okay, so this is, so this, I'll just write the formula here. Okay, so standard formula and derivatives. Or differentiation. So I think you will be aware of this rule. So division rule, it is called a division rule. Okay, if you are taking the derivative of this d by dx of the ratio of two functions, that is u of x divided by p of x, so that will be equal to v of x into d by dx of u of x minus u of x into d by dx of v of x whole divided by v of x the whole square. Okay, so this is a standard formula in differentiation, that is differential calculus. This you have to remember. Okay, so this is the formula. Okay, that same formula I am applying here. Okay, so to find out this d phi x of omega divided by d omega. Okay, here I am taking derivative with respect to omega. Okay, so we can just verify that this is the final result. Okay, so now what we are going to do, we are going to put omega equal to 0 in this expression. So we are going to take this entire expression. Okay, in that we are going to substitute omega equal to 0. Okay, so when you substitute omega equal to 0, what happens here? So this entire thing simplifies to a plus b. Okay, here you put 0, this becomes 1. Okay, here you put 0, everything goes away. Okay, so it is ja divided by 1 into jb divided by 1. Okay, so we can take j outside. Okay, so this is at omega equal to 0, this becomes just a plus b. Okay, so here we have one more, so here you have 1 minus j omega b the whole square. Okay, so here you put 0, this entire term goes away. So you have minus j power 1. Okay, so why does this minus j come? So that is the term that is present in the formula. Okay, so minus j power n. Okay, so since this is m1, we are taking minus j power 1 into this entire thing at omega equal to 0. So our thing reduces to a plus b, just a plus b. Okay, so now we are taking once again. Okay, so one more time we are taking the derivative. Okay, for each of these terms, so you have to take separate derivatives. Okay, so that I am taking here. Okay, you can go through these derivatives. Okay, so each term has two terms. Okay, so this generates 2 terms here, and this generates 2 terms, next to 2 terms. Okay, and then in this you have to substitute omega equal to 0 and multiply by minus j power 2. Okay, so it is the second derivative we are taking, it is minus j power 2 into d square phi x of omega divided by d omega square. That is, it is denoting the second derivative evaluated at omega equal to 0. So what we have is a square plus 2ab plus 2b square. Okay, just substitute omega equal to 0 in this entire expression, you will get this a square plus 2ab plus 2b square. Okay, so you can go through this slide later on. Okay, so I'll be sharing this slide in the class. Okay, you can go through the slide slowly. You can see you can write down the steps and check for yourself. Okay, so now we know what is this. What is this? This is m2. Okay, what is this one? This is m1. So we already have m2 and m1. Okay, so directly we can find what is mu2. So this is our mu2. That is sigma x square. That is equal to mu2. Okay, m2 minus m1 square. Okay, I am just evaluating this a square plus 2ab plus 2b square minus m1 square. That is a plus b whole square. What is this? This is actually a plus b whole square. Okay, there is a minus 7 outside. So you include all these things outside, inside. So you will cancel many terms. And finally, this is your mu2. Mu2 equal to b square. Okay. So is this same as our previous result using our direct method? Yes. So previously we used the direct method to find out this mu2. Okay, that was also b square. Here again using our characteristic function, we have arrived at the same value. Okay, so for mu2, this the simplicity of your characteristic function method will not be obvious to you. Okay, so when you go for mu3, mu4, mu5, etc., so that is bigger order moments, then you will see that this characteristic function makes it a lot more easier. Okay, okay, so yeah, so this is, so we'll stop with this. So just to summarize what we learned today. Okay, so we saw two examples. So a summary of what we learned today. So two examples of finding moments using the definition or direct method, using definition or direct method. Okay, so we observed that it is difficult. Okay, it is difficult for higher order moments. That is mu4, mu5, etc. and mu n. Okay, so we invented or we introduced. So we introduced easier method which are using our characteristic functions and moment generating functions. While write it in short form as MGF. Okay, so CF or MGF. Okay, so how do they make our job easy? They convert all the integrals into, so integration is eliminated. So derivatives are introduced. Okay, so integration is eliminated, means only one time we have to do the integration. Okay, so after that it is all only taking derivatives. Okay, so this is how they make our evaluation of moments easier. They introduce derivatives. Okay, so derivatives are easy compared to, so d by dx is easy, integration is difficult and time consuming. Okay, so by using derivatives, our characteristic function and moment generating function make easy the evaluation, make the evaluation of moments very easy. Okay, so you go through the slides. Okay, so there are a lot of steps involved. So I'm just giving, I'm just reducing the number of steps. Okay, so to cover more topic in this class, I'm reducing the number of steps. Okay, you have to go through the book I shared on calculus. Okay, and then you have to evaluate the problems here. Okay, so don't skip the revision. Okay, so every day you have to revise what is being taught. Okay, so that you are able to follow the topics throughout. Okay. Okay, so every day whatever is being taught, you compare the steps that are involving calculus. Okay, so you take the calculus book. Okay, so you follow which, means you find out which formula has been used in this particular step. Okay, and then you do the step yourself and check whether you are also getting the same answer that are shown in the slides. Okay, so that will be a practice for you in this calculus. Okay. Yes, I think it's time to leave. Okay. I think Meher, can you take the attendance?
Okay, sir.
Okay, you can send me notes. Okay, thank you.